Hello, my dear students. Welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe this channel and press the bell icon to get the regular updates of the upcoming lectures. My dear students, today's topic for the lecture is molecular orbitals. As the name suggests, we are going to study about the molecular orbitals. Now, as we all know, atoms combines to form the molecules. The same way, their atomic orbitals also intermix with each other to form the new set of orbitals called molecular orbitals. These molecular orbitals are different from the hybrid orbitals. In hybridization, we have done that the orbitals of same atom combines or intermix with each other to form the new set of orbitals called hybrid orbitals. But in case of molecular orbitals, the orbitals of two different atoms of same element or different element will intermix with each other to form the new set of orbitals called molecular orbitals. Now, molecular orbital theory is only applicable to the diatomic molecules like F2, Cl2, Br2, I2, N2, O2, etc., whereas hybridization starts from the triatomic molecules. Now let's move to the screen for the detailed lecture. Why there's a need for molecular orbital theory? Let us start from here only. Molecular orbital theory. So I'm writing why there's a need to study molecular orbital theory. I'm starting this topic from this question. Why there's a need to study molecular orbital theory? Its answer is I'm explaining its answer with the help of an example. Let's take an example O2 molecule. O2 molecule. Let's make its Lewis structure. Hold on a second. Now, let's make its Lewis structure. That's the oxygen and the oxygen. How many valence electron are there in oxygen? It's 6. So I'm marking the electrons around the first oxygen, the first electron, second, third, fourth, fifth, and the sixth. Now let's come to the second oxygen. That's the first electron, second electron, third electron, fourth electron, fifth electron, and the sixth electron. Now we all know that oxygen form two bonds with each other. So that's our first covalent bond and that's our second covalent bond. So we got double bond between two oxygen atoms. So we got the first bond pair of electron. That's the second bond pair of electron. Now this is the lone pair of electron. Again this is the lone pair of electron. That's again lone pair of electron, and that's again lone pair of electron. Now here we are having all the electrons in pairs. We are having two bond pairs and the four lone pairs in O2 molecule. As all the electrons are paired, as all the electrons are paired, due to which what's gonna happen? It signifies that O2 molecule will not be attracted by magnetic field. Whenever any chemical compound is not attracted by magnetic field, then that substances or that molecules or that compounds are referred to as diamagnetic substances. So O2 is expected to be diamagnetic substance because it will not get attracted in magnetic field, and that's according to the theoretical concept. So O2 molecule will not be sorry so the O2 molecule will be regarded as diamagnetic substance. So the O2 molecule will be regarded as diamagnetic substance. But in reality, O2 molecule gets attracted in magnetic field hence O2 is a paramagnetic substance in reality. According to theoretical concept, O2 is expected to be diamagnetic. That is, it will not get attracted in magnetic field because all the electrons of O2 molecules are paired. But in reality, O2 found to be paramagnetic. That means it gets attracted by magnetic field. What's the condition for any chemical compound to get attracted by the magnetic field? It's that molecule must have some unpaired electrons. At least one electron unpaired must be there. Only then that substance will get attracted in the magnetic field. So that means O2 is somewhere having unpaired electrons, but Lewis structure is not signifying that unpaired electrons. So to find that unpaired electrons, there's a new concept called molecular orbital theory which has been introduced, and this molecular orbital theory deals with diamagnetic substances, that's O2, Cl2, Br2, I2, N2, CnCO, etc. Now, let's start in detail about molecular orbital theory. So from this point I'm starting molecular orbital theory. Now, we all know atoms combines to form molecules. Atoms combines to form molecules. That means their atomic orbitals, their atomic orbitals will also combine to form molecular orbitals. So their atomic orbitals will also combine to form molecular orbitals. Now, we all know in orbitals electron moves in the wave form. I'm writing in atomic orbitals, comma, the electrons moves in a waveform. That means when two atomic orbitals will intermix with each other, then there will be the addition of the waves of two electrons. So the addition of waves of two electrons will be understood by the topic called interference. So that's the topic called interference, and we are going to deal it with detail. Now I'm starting a topic called interference. Interference. I'm writing it is the phenomena. It is the phenomena of addition of two waves. Now, as electrons are moving in the wave form in the atomic orbitals, and now two atomic orbitals are combining containing one electron each, so that means two waves, the two electronic waves are going to be added. For that thing we have to deal with the phenomenon called interference. Now, interference is of two types. The one is constructive interference and the another is destructive interference. The first one is constructive interference. What is constructive interference? It is the addition of two waves which are in phase. In phase stands for, assume this is the one wave and this is the another wave. Now, here you can easily justify that crest is overlapping, the crest of first wave is overlapping with the crest of second wave, and trough of first wave is overlapping with the trough of second wave. So it's the in phase. The two waves are in phase, and the addition of two waves which are in phase is called the constructive interference. So what will happen? There will be increase of amplitude. So that's our resultant wave now with increased amplitude, but wavelength will remain same. So constructive interference will result in the formation of new wave with greater amplitude but with the same wavelength. So when the two atomic orbitals are combining and the electrons which are present in both the atomic orbitals are moving in a wave form and that two waves are in phase to each other, then there is a phenomenon called constructive interference which will result in the formation of bonding molecular orbitals. By the phenomenon of constructive interference, we are going to have the molecular orbital called bonding molecular orbital. I'm repeating it again. When the two atomic orbitals are mixing with each other, then the electrons are there. Electrons moves in the wave form. When the two waves of both the electrons are in phase, then the phenomenon called constructive interference will occur, which will result in the formation of new wave with a greater amplitude but with same wavelength, and it will result in the formation of new molecular orbital, which is termed as bonding molecular orbital. And bonding molecular orbitals always favors the formation of the bond. I'm writing always favors formation of bonds. Now, let's move to the another type of interference called destructive interference. Now it's destructive interference. Now, again, it is the addition of two electronic waves of two different atomic orbitals of different atoms, but these two waves are out phase. I'm again writing. It is the addition of two waves which are out phase. Let me show you with the help of the diagram. This is the first wave and this is the second wave. Here you can observe that crest of first wave is overlapping with the trough of second wave, and the trough of first wave is overlapping with the crest of second wave. So these waves are out waves, due to which what's going to happen? There will be the cancellation of amplitude. There will be the cancellation of amplitude but with same wavelength. So this type of interference, that means destructive interference in which the two waves are out phase, will form the molecular orbitals which will be termed as anti-bonding molecular orbitals. I'm repeating, two atomic orbitals containing one electron each, and both the electrons are moving in wave form but in out phase, which will result in the formation of new molecular orbital, and that will be termed as anti-bonding molecular orbital. So we got anti-bonding molecular orbital, and anti-bonding molecular orbital does not favors bond formation. I'm writing, it does not favors formation of bonds. So that's all about the interference. Now I'm going to make the orbital diagrams of overlapping of 1s and 1s, sorry, intermixing of 1s and 1s, intermixing of 2s, 2s, and intermixing of 2p and a 2p. Let's make it. Now, Let's start with the orbital diagrams. So, first case. This is the nucleus of first atom, and that's the s orbital, plus that's the nucleus of second atom, and that's the s orbital. Now we know that s and s orbitals always forms sigma bonds. So now there is a mixing of s and s orbitals, and we are going to have the first bonding molecular orbital. These are the two nucleus, and that's the new shape of new bonding molecular orbital. And this has been formed s and s orbital, sorry, forms sigma bond. So this will be termed as sigma s orbital. If it's 1s, then this will be called as sigma 1s molecular orbital. Sigma, why sigma? Because s and s orbital always overlaps to form the sigma bonds. If it's 2s, then it is sigma 2s. The molecular orbital will be named as sigma 2s. Now, we got the first bonding molecular orbital. Now, let's come to the second case. That's the nucleus. That's again 1s. For simplicity, I'm mentioning minus in between to make you understand. Now I'm talking about the anti-bonding molecular orbital. That's again nucleus, and we got the assume 1s over here. Now there will be the sorry, there will be again the formation of molecular orbital, and that will be now anti-bonding molecular orbital. Now that's the nucleus of the first atom, that's the nucleus of second atom. We got the lobes over here and over here. In between, we got the nodal plane. Nodal plane. What is nodal plane? It is the region around nucleus where probability of finding electron is 0. Now, this is anti-bonding molecular orbital. So now I'm writing again sigma because s and s orbitals always form sigma bonds. I'm mentioning star over here. This star will signify that this is anti-bonding molecular orbital. So that's sigma star 1s. Sigma star, that is anti-bonding molecular orbital. I'm writing it's anti-bonding molecular orbital. So that's the orbital diagram. Now I'm making one simple diagram to be used to fill the electrons. Here we got the 1s of first atom. There we got the 1s of second atom. When two atomic orbitals will mix, we will have the two possibilities. The one is the sigma 1s, the bonding molecular orbital, and the another is sigma star 1s, the anti-bonding molecular orbital. So let's make it, and you have to make it like that's sigma 1s, and that's sigma star 1s. And the energy of anti-bonding molecular orbital is always greater than the bonding molecular orbital. So I'm writing energy order, that's sigma star 1s will have greater energy than sigma 1s. Sigma 1s has lower energy, that's why it will favor the bonding. Sigma star 1s has higher energy, so it will not favor bonding. A very simple rule. Now, that's all about the mixing of s atomic orbital to form the molecular orbitals. Now, let's move to the p orbitals. In p orbitals, I have told you in the previous lectures, in p subshell. In p subshell, we have three orbitals. That's px, py, and pz. Px, py, and pz. Out of these three, one will form sigma bond and another two will form pi bond. And specifically, here this pz will form sigma bond and px and py will form pi bond. So now let's have this case. So that's the nucleus of first atom. That's pz. Let us mention the signs. That's the minus, or we can say plus. Now, again pz of the another atom, and I'm again mentioning the sign on the lobes. That's the plus and the minus. Now, when the two lobes of same sign will overlap, then bonding molecular orbital will form. So that's the first nucleus, and that's our second nucleus. The two lobes got fused of same sign, and we got the smaller lobes over here and the here. So we got first bonding molecular orbital, that's sigma, take it to be 2pz, that's sigma 2pz, and its bonding molecular orbital. Now, let's move to the anti-bonding molecular orbital now. That's again p minus plus, and that's again p of another atom, that's again minus plus. Now in this case, there is intermixing of two lobes with opposite sign, which will favor the formation of anti-bonding molecular orbitals. So we're gonna have, that's the nucleus of first atom, that's the nucleus of second atom. We got the first lobe, the second lobe with a plus sign, and the third lobe, third lobe, minus, minus, plus. Here also we got the nodal plane. And now it's sigma star 2p z, that's anti-bonding molecular orbital. So we got the bonding molecular orbital and anti-bonding molecular orbital for the p orbitals which will form sigma bonds. Now let's move to the bonding and anti-bonding molecular orbitals for p orbitals again forming pi bonds. Now that's the nucleus. We all know pi bonds are formed by the lateral or sidewise overlap. Now it's the second orbital of p. Here that's the plus, minus, that's again positive lobe, negative lobe. So here will be the sidewise overlap. So that's the nucleus of first atom, that's the nucleus of second atom. The lobes with same sign fused to form the bigger lobe with a plus sign, and here we got the second lobe with the negative sign. So that's the pi 2p x or pi 2p y. Now, and that's the bonding molecular orbital. Now let's move to the anti-bonding now. That's the lobe with plus sign. Here's the lobe with negative sign. That's the lobe with negative sign. And that's the lobe of plus sign. Now, that's the nucleus of first atom. That's the nucleus of second atom. We got one lobe over here. We got second lobe over here. That's the third lobe over here. And the fourth lobe over here. Plus, minus, plus, minus. And we got, that's the pi star now because it's an anti-bonding molecular orbital. Pi star 2px, or we can say pi star 2py, and that's the anti-bonding molecular orbital. In this case, we are going to have two nodal planes. So that's the first nodal plane, and that's the second nodal plane. We got the two nodal planes. Now let's make a structure, the simple structure. That's the p subshell of the first atom. And we are having three p orbitals. That's 2px, 2py, 2pz. And that's another atom. P subshell 2px, 2py, 2pz. Now, we know that 2pz and 2pz is gonna form sigma bond, and is gonna form two molecular orbitals, the sigma 2pz and sigma star 2pz. So I'm making them, oops, sorry. We got the sigma 2pz, and that's sigma star 2pz. Now, firstly, we got the bonding and anti-bonding molecular orbitals for sigma bonds. Now let's move to the pi bonds now. We got the pi 2px and pi 2py. The energy of pi 2px and pi 2py is almost equal. So we make these two molecular orbitals, these two bonding molecular orbitals together. So like this, and we got it like this. Now, the anti-bonding anti-bonding molecular orbitals forming pi bonds. We got pi star 2px, and that's our pi star 2py, and these are anti-bonding molecular orbitals. So this is the molecular orbital diagram for the p subshell having three orbitals, 2px, 2py and the 2pz. Now, energy order. Energy order is sigma 2pz is of the lowest energy, then pi 2px, pi 2py have somewhat greater energy. Then there's a turn of anti-bonding now. Pi star 2px and pi star 2py further have more energy. And lastly, sigma star 2pz will have the highest energy. Now, but this energy order will be applicable for oxygen, that's O2 molecule, fluorine, that's F2 molecule. For nitrogen, there is a minor change. For atomic numbers 1 to 7, the energy order will be sigma 2pz will have lower energy. Sorry, pi 2px and pi 2py will have the lowest energy. Then there's a turn of sigma 2pz. Then there's a turn of pi star 2px and pi star 2py. And lastly, there's a turn of sigma star 2pz. So, this is the case for molecular orbital theory. Now let's come to the very first question which I have written. Why there's a need to study molecular orbital theory? Because we found O2 to be paramagnetic. So that means we need to now fill the electrons in these diagrams, to find out how many unpaired electrons does O2 molecule have. So there are certain set of rules to fill the electrons in molecular orbitals according to their energy orders, which we will be doing in the next lecture. So stay tuned. So that's all about molecular orbital theory, where we came to know that two atomic orbitals of two different atoms of same or different elements combines with each other to form two types of molecular orbitals. One is the bonding molecular orbital, which have been formed by constructive interference of the electronic waves, and the another one is anti-bonding molecular orbital, which have been formed by destructive interference of the electronic waves. The bonding molecular orbital will favor the formation of bond, whereas anti-bonding molecular orbital will not favor the formation of bond. So, if any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture and also in the description of this lecture. Please do like, subscribe and share this channel to maximum number of students. Concepts of Chemistry by Amit Verma.